Hello. Hello. In this video, we want to talk about limits and their applications. So we want to discuss the concept of limits and how limits can be applied. Limits, by introduction, help us model and solve many real-world problems where things are approaching a value but not necessarily actually reaching that value. In physics, engineering, biology, economics, limits describe instantaneous changes, long-term behaviors, critical points, and infinite processes. So the key idea is that limits describe what happens as we get very close to a particular thing or point or condition, not necessarily what happens exactly at that point. Like our aspiration in life is to get to a level, but as we continue to, move towards that point, our demands, our needs become enlarged. So human wants are limited, and so we cannot reach all our limits. We cannot reach, all our needs. We cannot achieve all our earthly goals. So that's a very good example of limits. Okay. Now, significance of limits in real life. What are the importances of limits in our life? Well, it can be used to predict future behavior like population, markets, situation. 2, it can be used to understand instantaneous rates. For example, speed, growths, and so on. 3, you can use it to design stable systems like bridges in engineering, circuits, and the like. 4, we can use it to optimize resources like minimum cost, trying to, when you're optimizing, you are trying to find the minimum cost, the factor of production that can be used in such a way that you will spend much and achieve greater. To model extreme scenarios, e.g. black holes, maximum stress, and just to mention a few. Now, what are the steps we could take to solve real-world problems using limits? Because there are so many real-world problems that we can solve using limits. So limits is a vital tool in mathematics that can be used to solve various real-life problems. In this video, I'm going to expose us to so many real-life problems that we can use limits to solve. Don't forget, I remain Dr. O.J. Ogunshola. Now, the first step is you identify the quantity that changes. What are the quantities that changes? Distance can change, time can change, temperature can change. Look at, first of all, you have to identify them. 2, you formulate the function describing the relationship between these parameters. 3, you set up the limit equation or limit expression depending on the question. Depending on the question you want to solve. E.g., as a time approaches infinity, or as a value approaches a boundary. You do that. 4, you evaluate the limits using algebraic techniques, and graphs or estimation. And 5, you interpret the result carefully in the context of the problem. So those are the steps that could be taken when you are trying to use limit to solve everyday problem. So now we start with an instantaneous problem. Let's start with an instantaneous problem and see how it could be used. How limits could be used to solve the problem. Let's see how limits could be used to solve the problem. Now, example 1. This is going to be instantaneous speed. Example 1. Example 1. Instantaneous speed of a car. That's instantaneous speed of a car. Now, this is the movement of a car at an instance. Okay, now let's look at the problem. Every day we see a car moving on the road, and the like, express and the way. So we said limits can be used to solve everyday problems. So this is one of the everyday problems we encounter, we see daily. There's no way you go out one day, or whether you travel or you move around, you will definitely see a car moving. So one of the problems we can use limit to solve is instantaneous speed of a car. That is the speed of a car at an instance. How does a car move? What position does the car reach after a particular period of time? So let's look at a car's position. A car's position, this is in physics, at time t, that is in seconds, is given by, let's look at the equation of the car. S of t, this is an equation, is equal to 5t squared meters. So suppose we are given this equation, we are now asked to find the instantaneous speed at t equals to 3. That is, when the time is equals to 3, what will be the speed of the car? Okay, now how do we solve this? To solve this problem of instantaneous speed, we are going to use derivative, we are going to use limits. We're going to use limits. Instantaneous speed will be equal to derivative, which is the limit of average speed. Instantaneous speed is equal to the derivative equals to average, the speed of average speed. Average speed rather. Average speed. That's what by instantaneous, that is the limit, average speed limit. Average speed limit. Sorry about that. Okay? Average speed limit. Now, how do we find the average speed limit? Now, to find the average speed limit, we are going to apply this formula. You must have said that is equal to derivative. What's the derivative of the function? I hope you can still remember. In your calculus, before a function could be differentiable, before you can get the differentiation of the function, the limit of that function must exist. So to find the derivative, which is the same thing as average limit, that will be equal to what? The speed speed at t equals to 3 will now be equal to the limit as h tends to 0 of, let's say, s of 3 plus h minus the s of 3 all over h. This is exactly the definition of a derivative. So I told you instantaneous speed is equal to derivative, same thing, and the same thing as average speed limit. So, and the question says we should find the speed at t as t equals to 3. So which is the same thing as limit of the derivative. This derivative of s at 3. That's it. Okay, now how do we go about this? Let's find using the given problems to find the derivative. You know, we are given that our s of t is equal to 5t squared. I think that's what we are given. Beautiful. So now s over 3 plus h now. So that is when our t is equal to 3 plus h. That will be equal to what? Using this one, 5 into our s of 3, that is like s of t. When the time is 3 plus h. I hope you are getting it now. This is meaning of s of t minus s of t. When t is 3 here, when t is... You know, why do we put 3 plus h? You know, when a vehicle moves from one point and stop after a few seconds, it must have extended its movement. Its movement must have moved from one instant to another. It must have exhibited what we call speed. It's no longer at uniform speed. At initial speed. It has moved beyond that initial point. So that's why we are adding, this is an extension. This h is the change, that occurs when the speed is changed. When it's instant, we're at the point of this instantaneous point has changed. So it exhibits an increment. So that will be what? S of t, which is s of 3 plus h now, which is now our t is, s of t from that formula is t squared. So that what? 3 plus h squared. Okay? Now, that implies that 5 of, when you find the square of this, we have what? 3 times h times 2. That is what? 6h. Sorry, let's start with this. 3 squared is 9 plus 6h plus h squared. Okay? So that is the value for that one. Now, which is, if by extension, if we extend this, multiply out, we go to 45 plus 30h plus 5h squared. Now, when is it s of 3? When the time is 3. That is when s of t is 3. So what do we have? Now, we will put 3 instead of t now. That is 5 into 3 squared. Okay? 5 into 3 squared. That will be what? 5 times 9. And that will be 45. So now we now plug in the formula and the values inside the formula. So let's plug in the values. We have obtained individual values there. So we plug it in. Let's plug it in. So by the time you plug it in, you will have, the first one is what? That will be limits as h tends to 0 of what we obtained there. We have 45 plus 30h plus 5h squared. That's what we obtained. Then minus, this one gives us 45 all over h. So 45, we cancel 45. So we'll be left with what? Limit as h tends to 0 of what do you have now? 5h squared plus 30h all over h. Okay? I hope you are we following? Beautiful. So by the time you now, what is common there is say limit as h tends to 0 of h is common. You have 5h plus 30 all over h. This h will cancel this h. So you'll be left with what? You'll be left with what? Limit of 5h plus 30. So as h tends to 0. So if h tends to 0 here, we have what? 5 times 0 plus 30. So which is going to what? 30. So the instantaneous speed here is 30 meters. So you have 30 meter per second because that's the rate of change of the vehicle's speed with time. So it's going to be 30 meter per second. So that's that about that. Now let's go to another example. Let's go to another example, still showing the application of limits in everyday's life. Here we have shown the application of limits, at an instance of a car moving, a moving car, and that is in physics. Okay, we have used this illustration to substantiate limits application in physics. Now let's go to the application of limits also in medical sciences, like biological, setup and the like. Hospitals, medicine, pharmacies, the like. So this time the second one is going to be drug concentration over time. I want to look at application of limits in this area of drug concentration over time. The problem, let's look at the problem there. The problem says the concentration C of T in milligram per liter, in milligram mg per liter of a drug in the bloodstream is this is given by, let's look at the C of T equals to 100 T all over 5 plus T. That's the equation. That's the expression connecting the concentration with respect to time. So concentration here is a function of time. Okay, what happens? The question now says, what happens to the concentration? What happens to the concentration as T tends to infinity? That is a long time after taking the drug. When I say T tends to infinity, that is what happens to the concentration as T tends to infinity means a long time after the person or the patient has taken the drug. So now let's look at this solution. Now the function given is concentration depending on time is 100 T all over 5 plus T. Now we are asked to find the concentration as T tends to, that is, we are asked to say that find limits as T tends to infinity, of 100 T all over 5 plus T. So what you just need to do without wasting your time is you apply the concept of L'Hospital's rule here, because you are taking limit tending to infinity, and applying L'Hospital's rule here simply means that you look for the variable T, divide numerator and denominator by T, and now take the limits. So from there you get the result. Okay, let's look at that. So that will be 100 T all over 5 all over T plus T all over T. I believe you understand. That is, for you to take T to infinity, divide the numerator here by T, divide the denominator by T. So this one will cancel this one. You have 100 all over 5 over T plus 1. Yes, that will be that. So now you take your limit. You can now take your limit. So taking limit now means, now limit as T tends to infinity, that will be of 100 over 5 over T plus 1. That will be what? 100 over 5 over infinity plus 1. This will be 0. And you divide a number by infinity with just 0. 100 over 1, because 0 plus 1 is 1, which is 100. So you get 100 milligram, because the unit given milligram per liter. So that's the result. So that means after a long time that the patient has been taking that drug, at the point in time, the drug will have concentrated to 100 milligram per liter in his or her system. So that is another example of application of limits in everyday life. Another application of limits in everyday life is in an object approaching a maximum height. Maybe you throw an object up and you are asked to find the maximum height of the object or the speed reached by the object in the air. So this is another example of how limits can be applied in everyday life. Let's look at the problem there. A ball is thrown into the air. A ball is thrown into the air. Its height h of t, that is h as a function of t, in meters. After t seconds is h of t is equal to minus 4.9 t squared plus 19.6 t. Now find the height of the ball. Find the height of the ball. Or find the height of the ball rather. Find the height of the ball. Find the height the ball approaches at the top of its flight. Now, when the ball is thrown into the air, it must get to a level before it falls down. Okay. So the ball is thrown into the air. Its height in meters after t seconds is given by this equation. Height is a function of time. Now, the question says find the height the ball approaches at the top of its flight. Okay, let's solve this. They're still going to use limit here. Yes. Let's clean it up and solve, please. Let's clean up and solve. Now we solve this. Now the top happens when the velocity is 0 and the velocity is derivative of height. So the object reaches the top of the height when the velocity becomes 0. So let's say that we have the velocity of the object, which is what? The derivative of the height. So we now differentiate the height given. The height given is minus 4.9 t squared plus 19.6 t. So you differentiate that. You have minus 9.8 t plus 19.6. So that is it, to get the velocity the object reaches in the air. That's the derivative of the function height. I hope you understand. The question says find the height the ball reaches, or the height the ball approaches at the top of the flight. So, and that is, we are asked to find the velocity, which is just the derivative of the height. Differentiating this, we have minus 9.8t, then plus 19.6. Fine. So now setting v of t to be 0. That is, when the ball reaches the maximum height, the final velocity is equal to 0. So we have 0 will be equals to minus 9.8t plus 19.6. So by the time you bring this one here, you have 9.8t equals to 19.6. So how do you get t?
Divide both sides by 9.8. You have t equals to 19.6 all over 9.8. And that will give you what? 2 seconds.
That will give us 2 seconds. Okay? So now, h of t, which is given as minus 4.9 t squared plus 19.6 t will be minus 4.9. Our t is now 2 squared plus 19.6 times 2. And so that is when you multiply that, you have what? When you multiply this, minus 4.9 t squared plus this, the total thing you're going to have is 19.6 meter. Try that. So that is that about finding the velocity, or the height rather, the height the ball reaches when it gets to the maximum height. You can see how we have used limit there to solve that. Now another application of limits. Another application of limits. You can see limit is so much applicable in our day-to-day activities in life. So this time around, we want to look at the application of limits in cooling. Application of limits in cooling. As cooling, that's number 4. Cooling a hot object. Cooling a hot object. That's from Newton's law of cooling. Newton's law of cooling. Cooling a hot object. Newton's law of cooling. Okay. Let's look at the problem. A cup of tea or a cup of coffee, let's use coffee, is cooling. Its temperature T of T in degrees Celsius after T minutes is given as T of T is equal to 20 plus 60 exponential minus 0.05 t. Find the temperature. Find the temperature as t tends to infinity. Beautiful. To find the temperature as t tends to infinity. So, what are we asked to find there? Just find the limits. So, that is, we have to take the limit as t tends to infinity of the given function, 20 plus 60 exponential minus 0.05 t. So, now means at this point now, if we look at the problems now, what we are just asked to find is the temperature. And this expression is expressed in form of temperature as a function of time. And the value for temperature as a function of time is given to be 20 plus 60 exponential minus 0.05 t. So, as t now tends to infinity, we have what? 20 plus 60 exponential minus 0.05 with respect to the multiply by what? By t to be infinity. And when you multiply everything here, you're multiplying that this value 0.05, multiply by 5, multiply by infinity, everything here will be 0. Hence, that is exponential. What you have here is 0 automatically. Yes, exponential minus 0.05 infinity will be 0. So 0 times 60, that's 0. That's what? 20 plus 0, which is what? 20 degrees Celsius, according to that's degree Celsius. So the temperature of that particular object in degrees Celsius will be what? Be 20. Now, lastly, let's look at another application. You can see how we have been able to see the application of, we have been able to show the application of limits in everyday life. Limits in action, limits in everyday life. Okay? Yes.
The last one here, we talk about, let's look at application of limit in economics. That is number 5, cost per item. Cost per item in mass production. Cost per item in mass production. So I want to look at application of limits in that aspect too, which is economics. Now let's look at the problem there. Problem. The cost C of X to produce X units of a product is given as the cost with respect to, that is the cost as a function of X, is equal to 5,000 plus 2X. Now find the average cost per item. Find the average cost per item as X tends to infinity. Beautiful. Now look at this very simple example. If the cost of producing X units of a product is this, and you have to find the average cost, that means to find the average cost per item, you just have to divide the total cost by the unit cost, or by the number of units. So that means you are finding what? C of X over X. Okay, first of all, find C of X over X, now find the limit. That will be what? 5,000 all over X plus 2X all over X. Okay? Yes. So that is to find the average cost of the product. But as X tends to infinity, what are we going to get? So now implies limits as X tends to infinity of what? C of X all over X. So that would be what? That would be let's do it here. That would be okay. And C of X over X is what? 5,000 all over X. That is the limit of X as X tends to infinity of 5,000 over X plus this one will be 2. This cancels this 2. So that means we're going to have what? 5,000 all over infinity plus 2, because this one does not have X. So, and anything you divide by infinity will be 0 plus 2. So when you 0 plus 2 will be what? 0 plus 2 will be what now? Will be 2. So that means the cost is 2. So what is the cost is measured in what? The cost is measured in so the average cost approaches, let's say, the unit of the cost produces, we are not told whether, the unit of measurement. So let's say the average cost approaches, you can use dollar, you can use naira, $2 per item. So we assume that dollar is the unit of the price, of the name of the price used here. It could be naira, it could be anything. Let's assume this we use the cost is in dollar. So the average cost approaches $2 per item. So on this note, we have come to the end of the application of limits in our everyday life. Do well to click on the notification bell so that each time I upload a video, you'll be notified. Thank you.